I will talk about more general things than the title. The title, Giant Exciton funnel resonances in tantalum nickel selenide, just reflects, underlines one of the main observations and findings of our comparative studies of both tantalum nickel selenide and tantalum nickel sulfide compounds. This work is a result of collaborative efforts between two departments of Max Planck Institute in Stuttgart, headed by Bertenheim and Hide Takagi. Timothy Larkin contributed the experimental part of this work. Larkin is not the unique family in Russia, but nevertheless, he's the younger generation of the same family, you know. His grandson. Yeah. And it was really I was really very lucky to discuss our results with Konstantin Kikoin, who was the Emmanuel Rajba student, and he was the one who actually pointed out that our result can be explained and understood in terms of Rajba antenna effect. Unfortunately, he passed away shortly after our first publication was submitted. So, and we followed quite traditional experimental spectroscopy approach, and it's linear response at equilibrium, far field, no cavities, sorry, and it's just maybe these days it's quite boring, but in order to build a story, we have to start from the groundwork. Yeah. So, and we used quite accurate measurements, quite accurate techniques. It's wideband terahertz from terahertz to EV ellipsometry. We cover spectral ranges of phonons and absorption edges and interband transitions from terahertz to deep UV. Spectral range, always by ellipsometry. And in my talk, I will focus, chain structure of this compound actually gives rise to very strongly unazoted pure electrodynamics of these materials, but in the following I will focus on this component of the complex directive function, which is related to the phonons polarized along the chains, just along the chains. Okay, and let me just compare these two materials for whole spectral range at intermediate temperature. I selected this temperature on purpose. I will explain why in the following. So, but nevertheless, you can see that both spectra of optical connectivity seem to be very similar. So even more, so you can really understand that because of electronegativity of sulfur ion and because of shorter bonds between sulfur and tantalum, because of stronger hybridization in valence bands between tantal 3D and sulfur band, all this effect make a larger difference, energy difference between valence and conduction band. But let me just renormalize by 12%, and then you can even see that all bands are at the same place, except some additional splitting of narrow subbands in these sets, and the optical band which forms the absorption edge is much stronger in the case of selenium compound. Nevertheless, you can also find that renormalized optical gap is almost the same in both compounds. It's quite counterintuitive to believe that the ground state and the origin of these bands are so different as believed these days. So it's believed that in one...
Can you just go back? So when you say the gap, which is 180 to 200, it looks like the first lowest feature is still somewhat higher in the red curve, the sulfur curve, than the selenium curve.
Usually, I mean, so it's consistent.
Oh, you mean just the place where the absorption becomes first different from zero?
Absolutely.
I understand what you're saying.
Yeah.
Okay.
Just following the frequency dependence of the band and Urbach tail there.
But I mean, so on that comment, so the first bump that one sees, so the big blue bump at the lower diagonal, about a little bit above the band gap. So that is a density of states feature?
Yeah.
Or that is an excitonic edge? Or?
I will show later.
Ah,
So
okay.
it's,
Yeah, right.
so, and then I don't really need to repeat the same arguments as Eduard already mentioned. So what grounds we have to believe that the origin of the gap in these two compounds is different. So first of all, because of the structural transition appeared there, and this structural transition actually could be tuned by a change in gap energy. So this energy is activation energy for transport measured at very high temperature, and then it means in orthorhombic structure for both compounds, and then you can see crossover from zero gap up to finite gap in a sulfur compound. So, and then I will compare these two compounds. We tried to measure in between, but it's because of substitution, chemically the sample become rather dirty. So then the next question is, if you try to explain in band structure calculations, so DFT calculations do not really give you, they do give you metallic solution only, yeah? So for both compounds. So, and then Hubbard 2 doesn't help you because you have empty and completely filled shells. And then what trick we can follow, so, and that's where he actually followed some tricks, following the approach of Trein Blacher from Vienna, using probably the Wiener code, and they use semi-local exchange potential instead. And then just with appropriate choice of parameters, they found they got actually solution which is metallic for orthorhombic phase of tantalum nickel selenide and still insulating for tantalum nickel sulfide. So I cannot really evaluate if these particular used parameters justified microscopically or not, but at least I can appreciate, okay, we have this problem solved now, yeah, these days. Then let's look at the temperature dependence, and you can find that very strong anomalous temperature dependence are all peaks over the whole spectral range for both compounds, and this temperature dependence of interband transition above 1 eV and all these transitions actually exhibit the same behavior, and position and peak positions and peak widths can follow temperature dependence, which is actually proportional to the Bose-Einstein factor phonon density for phonons with characteristic energies of about 50 for selenium compound and 20 for sulfur compound. It's quite well understood because of square root of ratio of masses. So then it implies that we have really strong electron-phonon coupling in this material. So let me just turn to low energies at the absorption edge. Here you can find that tantalum nickel sulfide does not really exhibit strong temperature dependence, which is really in contrast to what actually really happens in the case of tantalum nickel selenide. But nevertheless, you can really quantify how much, what's the density of electrons within these bands, and then you can find it's really huge strength. It's really, you have almost 1 electron per nickel in the case of tantalum nickel selenide, and it's essentially to assign it to direct transitions between these bands. So it's twice smaller in the case of sulfur compound. But nevertheless, if you then let's just consider this temperature dependence we found for tantalum nickel selenide, and it follows the same temperature dependence for the top valence band observed by ARGUS regarding broadening and shift of the band toward the Fermi level. I'm not sure about calibration of ARGUS measurements, but what I'm really sure, so that if you really consider the gap value with respect to the activation DC energy, then you can really find that it's just half. DC activation energy, just really half of that. It's 1000 K, so 1000 K, it's exactly 0.16, 0.17, 170 millieV. So it means we have rather good, yeah?
So another question, I noticed that the dielectric constant seems to be getting very large because this is a strongly dipole active transition, right? So are there measurements at lower frequencies looking for ferroelectricity or likely things there?
And yeah, you know that there is no negative contribution there. It's not metallic. So it's consistent with zero gap semiconductor, like.
Right, exactly. But it's just saying it's keeping going up and
going up. Yeah, it's going up.
So what happens?
So it's lowest temperature. You have. There is a gap. It's fine, but with increasing temperature, it reaches about 80. But I cannot. Yeah.
So this is optically. But if I were to go and measure at megahertz, what
I cannot really tell you exactly because it's not transparent. We tried with time domain spectroscopy, but we couldn't actually measure it. Could be, yeah. But
I'm just asking even at just sort of plain electrical measurements.
Yeah. No, we didn't actually follow. Then let me turn to the central point of my talk, probably, so which actually will give you some clear difference, not just quantitative but even qualitative difference between these two compounds.
Wait, I'm sorry, before you go on. So looking at this, I see that there's an onset of low frequency absorption at a temperature a little above 100 Kelvin, right?
Yeah.
That's where it
Yeah.
Is there anything observed in bulk at that temperature? I mean, I thought the putative excitonic insulator transition was at a higher temperature than that.
Transition temperature, yeah, we have a kink there, so it's consistent with DC transport, actually. It starts at temperatures of quite below the transition, but approaching the transition temperature, it speeds up, and then we have some kink there.
So the transition is visible as a kink.
It's visible.
In something
It's a
like,
kink, yeah.
But should I be surprised at the amount of low frequency absorption within the excitonic insulator state, or is that understandable in terms of a small gap or something?
At finite temperature, it should be there. So, but at lowest temperature, it's just a flat.
This is a quantitative question, but
Yeah,
all right. So
yeah.
I'm confused by a very stupid thing. What is the activation energy from resistivity?
From resistivity, activation is 1000 K, it's 80 milliV.
Yeah, okay. So the factor of 2 is on the other side. Right?
Yeah.
I mean, the activation energy
Oh.
of the optical gap, as you would.
Yeah, of course, yeah, sorry. Yeah, you're right.
Maybe.
But my answer is correct.
Sure.
But sorry, sorry, I didn't.
Maybe I can
I made a mistake, yeah.
briefly on this because you asked. I think it's still remarkable how much spectral rate is inside the gap, because it's something, okay, you could think that somebody you leap a little bit into the gap, but then if you would measure at very low frequencies, like at terahertz frequencies, it still should be fully transparent or whatever, because you have basically zero conductivity. But also, as Sasha said, we also tried, if you try to measure terahertz transmission on these samples, only below this 110-ish or whatever Kelvin, the sample really becomes transparent. And
Yeah.
of this, you really have rate
I will show
down
this
to
in-
terahertz frequencies. And
I will show this spectrum.
Okay, so that's to you somewhat surprising and not fully understood. Is that?
Yeah,
Okay.
where this rate in the low frequencies.
Yeah.
But if you look at this spectrum now, so for tantalum nickel sulfide, we overlooked first these features in spectra for selenium compound. It's a good reason for that. But nevertheless, if you look here, so for dielectric permittivity only, so we can find these two peaks rising with decreasing temperature below 150 Kelvin. It's really doublet feature. So, and one is weakly allowed, one is more allowed, and then it has funnel-like shape. It's extreme funnel-like shape here. So because it's consistent with steps in optical conductivity, it's opposite. You have peak in epsilon 1, we have step-like feature in sigma 1. Yeah, and then we can really see this doublet here. So now, if you look, once you already argued and you already convinced that we have these two features here, so you can really see that these two features can be really observed in this case as well. We believe that we have three criteria here, so but I cannot really give you numbers about excitonic binding energy because we have one-dimensional case, because we have we have position of these peaks superimposed on the sea of electron hole excitations. And this, the reason why we can see these two features on top of, above the onset of optical conductivity is probably because we have exciton-phonon complex there. So, but let me say that phonoresonances, exciton-phonoresonance by orders of magnitude lower energy is quite general feature of the optical absorption in long-dimensional semiconductors. And because if you apply a magnetic field, for instance, you can really form these excitons in high energy Landau levels, and then they start to interfere with the continuum. So it's naturally on top of the continuum there. Yeah.
Yes. If you do this, there is photoelectron spectroscopy on the sulfur compound in which you can have access to the real gap. And then you can estimate from there whether indeed you do have an exciton. Because what you are claiming is that you have those two excitons in the gap. And
no, it's not in the gap.
In the gap, they have very little oscillator strength, which will be against the concept of having a bound exciton inside the gap of a semiconductor.
This exciton is not inside the gap, I believe. That otherwise, we would not really see so strong interference with the continuum.
Continuous exciton.
So, picture now. So we have exciton feature here. Then we have we excite this exciton in the bound state with phonons, and then it phonons play the exciton states on top of the continuum, electron hole continuum, and they start to interfere. Yeah? And then why we have so strong quantum interference?
Where the electron hole continuum starts.
We believe that I already mentioned this 0.7 electron pinnacle site. It's electron hole continuum. It's direct excitation there, so between valence and conduction band. And this indeed, so absorption edge is here, but these two features are on top of the continuum. Something that actually places these two features on top of the continuum now. And then it's only like right now. This is the only actually mechanism how you play these excitons on the continuum.
So the point is that if you compare the two materials, what you see are two features, which however they're showing up in opposition actually in terms of conductivity and permittivity, and so you're associating that with Fano on the right-hand side.
And Fano there as well.
I see. So you think it's Fano it's just less
quality, less. Yeah. So I would expect less binding energy for selenium compound. Less binding energy probably because permittivity is 3 times lower. Yeah. As well, at least.
But the permittivity is actually again apparently associated with the transition itself.
Yeah. Exactly. Yeah.
So because it looks like. Well,
Yeah, okay, it's already a question. Yeah, but anyway, it's good to know that the gap energy is of about, of the same order. So it's good for us, yeah, so if we'd like to understand. Then different spectra, you can see very striking similarity now. So in different spectra, it's just raw data as measured, and then with increasing temperature above the base temperature, you can see the growing of this or suppression of this peak with increasing temperature. Yeah? And then you have this dispersive-like feature in delta sigma 1. In those cases, double feature here, and then you have peak-like feature in delta epsilon 1. So and then we followed rather standard phenological way to fit all this stuff, and then we mimic our electron hole continuum as a broad Lorentzian oscillator here, which is coupled with 2 excitons on top. And then we fit it quite well, and then we quantify these features, and we actually surprised, but you can really see already from raw data that in the case of tantalum-nickel selenide, we have really strong features there, so an effective number of electrons per nickel atom contributing to the quantum interference effect, and how actually they change the optical conductivity spectral at 0.26 electron per nickel, so which is 3-4 order of magnitude larger than phonoresonances in semiconductors and order of magnitude larger than in sulfur compound. The big difference you can already see in raw data. So here it's 40 in permittivity, here it's just 4.
So, sorry to interrupt. So let's see, we were just seeing sort of driven oscillations at 1 terahertz, right? So you're almost hitting that down at the bottom. Is there oscillator strength which is left over that you that you haven't seen yet?
No, no. It's
but it's not within your window, so it's not quite.
You mean the 1 tera?
No.
This is dipole allowed.
Oh, I see.
Yeah. So
Don't update your computer now.
there's another dipole allowed excitation at 4 millieV, which is 1 tera.
4 millieV.
sorry. Oops, it's again. Stop from here, yeah. So and then we come to how to explain it, and then Konstantin Korin actually he mentioned that we should really consider seriously giant oscillator strengths effect associated with the exciton complexes. And then it's really quantum cavity effect actually, so it's related to what we were talking about, but it's not optical cavity of course, it's polaron cavity, and then exciton oscillator strength, it's proportional to the ratio of the exciton size and volume of this cavity. Cavity means how far you can really feel the field of phonons. So but the difference now between selenium and sulfur compound, it's order of magnitude difference, and we believe that probably so we have this kind of exciton phonon complexes which are actually like droplets in the case of sulfur compound, and do not really produce long range distortion there, so but it's really consistent with the long-range monoclinic distortions related to formation.
Just to understand, if you
Can you go back? Yeah, maybe you can go back to previous slide. Yeah, basic.
here, because it's connected
yeah,
to.
exactly.
I think basically you're saying that there is sort of lattice self-trapping of the exciton.
Yeah.
That is what giving you these oscillators.
Mm-hmm. Mm-hmm.
This I'm happy. However, if that's the case, if you keep increasing the temperature or reducing, the coupling changes, and then you should see that this peak moves in position. It is really an exciton phonon coupling. And from your data, the only thing that you get is a broadening, not a move of the peak. Or
I cannot really follow temperature dependence of this peak because this peak disappears at 150 already. I cannot really see it. Yeah. Then, okay, if we believe that we have such kind of complexes, not connected complexes in tantalum,
so
sulfur
to make sure I
compound.
understand. So what you are saying is that this complex, I mean the oscillator strength is large, goes with the size of the cube of the size.
As actually, yeah.
Right. So the volume of the thing.
It's volume bigger, and then.
So your point is that in selenium.
In selenium, it's really extended.
The length,
Way,
so
yeah.
the length scale.
Yeah, absolutely, yes. Yeah, so.
Which is how long?
Yeah, I cannot really answer. I just say that it's order of magnitude difference between these two compounds, so that it's considered volume there. It's one-dimensional, so okay.
So one should be able to reveal that length scale from some experiment.
I will show you
the
something
argument that
else.
this is a one-dimensional exciton.
It's one-dimensional charge transfer exciton.
Sorry, but I mean, are you also, I mean, are you saying that this is really analogous to sort of charge-activating phase phonons as people did a long time ago in the 1D CDWs, where you basically light up a whole bunch of phonon modes because they're coupled to bound excitons, and they're dragged along. But those are normally at much lower frequencies, right? So that they...
Let me show you.
Oh, okay.
Sorry.
So what I actually mean, yeah, you're right. So in In the case of sulfur compound, you should see a soft mode there, so associated with internal excitations. Yeah? It's here. Yeah, it's along A-axis, it's along C-axis, nothing there, so but along A-axis you can really see very strong soft mode there at 10 milliV.
So what's the soft mode? Now I'm lost. What's the soft mode?
So you have internal interaction inside. So you have polaron, and then you have internal excitations, which actually at final frequency could be seen. Yeah, and then it's qualitatively different between these two compounds. In sulfur compound, we can really see this mode. Unfortunately, we cannot really follow this mode with the substitution of sulfur by selenium, and probably we would see how this mode actually softening. But what we are planning to do, we're planning to apply a strain, uniaxial strain, and look at this mode actually. Yeah?
So it is seen in sulfur. That's what you're saying.
This is sulfur. In sulfur, it's observed at finite frequency, and for sure, so you can really see here it's a peak in optical conductivity, and black line is dielectric permittivity, and phonons superimposed on this background. Phonons look like small featured gears on the background there. So along C-axis, you can really see just phonon there. So as expected from theory group analysis, you can find 4 beat 3U phonons for 8 polarization and 7 modes for C polarization. And then this mode is quite, its spectral weight, it's rather, I would say, it's reasonable actually if you consider, say, a peak in thermodynamic and specific heat, that the transition temperature is comparable already. But it's sulfur compound, no transition there. So it's always you have this local mode and you have local distortion only.
I mean, the point is, it's sort of if you were to interpret it as a phonon, it's a giant oscillator structure, phonon. But it's comparable to something which is electronic in character, which is usually what happens.
Yeah, but and then if you go from sulfur to selenium, what's going on there? So yeah, okay, this temperature dependence exhibit quite generic manifestation of unharmonicity. So and just hardening, softening, or broadening with increasing temperature. But then if you look at the phonons in tantal nickel selenide, you cannot really see any kind of local excitation soft mode there. So it's really clean. It's really clean, and even we use time-domain spectroscopy for clipped samples to measure transmission in this case, and to capture the first phonon of about 1 terahertz as discussed before. So, but it's infrared active. we have really good assignment because this mode becomes exhibit biaxial anisotropy now, and modes generic for C-axis B1U modes becomes B1 B3U and so on, and vice versa. And then it helps us to assign all these modes, and yeah, we did it quite well, but it's okay. We're quite confident with all these eigenpotents. And then looking at temperature dependence, everywhere you can see offset. So for clarity, for epsilon, sorry, I repeated. Oh no, yeah, okay. So and then for except you can clearly see gap filling, and for in the case of A-axis optical conductivity, all phonons become invisible already at high temperature, approaching the transition temperature. But then this phonon, which is active in both A and B and C polarization, along and perpendicular to the chains, you can clearly see how a gap starts to be filled by thermoactivated electrons, free electron there. So it's from the left side. Yeah? And then this mode becomes broader. Then I cannot really see it anymore. But I can guess that in the case of polarization of photons along A, along the chains, this mode should really follow some, I don't know, not other parameter, but at least it should really disappear in the orthorhombic structure. So certainly it should follow some anomalous temperature dependence. So, and it's really interesting mode because it's not really mode along A-axis, it's mostly some interchain coupling. So you have nickel chain static, and then tantal chains.
So this is the 1 terahertz mode that you are talking about.
This
so this is the same mode that
it's not exactly the same, but it's infrared active.
Yours is the Raman.
Yeah,
I see.
But energy is very close. But energy is very close. It's
Very
about
close indeed.
So, just final slide. So regarding the electronic background and filling of the gap, so we have two components. One is thermoactivated free electrons from left side, and then this polaronic-like behavior. So it's a mode which actually softening with increasing temperature and fill the gap. But still, yeah, and this temperature dependence is you can really see here. So regarding this epsilon 1 permittivity effect there, so it increases. Huh?
Just clearly I missed it. Where did you see the softening of the mode? The only thing you saw is the position of the peak, but not the softening. I mean, the only thing you see is that it loses oscillator strength. Or do I get it?
Oh yeah, okay. In this case, yeah. So no. Yeah, spectral weight is conserved. You're right. So it's just we can really see this increase in epsilon 1 there. So it's actually yeah. So roughly that's it. So and I try to convince you that in order to when studying electronic properties of this excitonic insulator candidates, it's very important. It's very important to follow comparative studies of both compounds to confirm the excitonic insulator hypothesis, actually. So it's really good that we have this reference object. Oops. Then in tantal nickel selenide, the giant spectral weight of the exciton phonoresonance due to antenna emission of large exciton phonon complexes imply that they are largely extended, overlapping and span the entire crystal along along chains, preserving the translation symmetry of the lattice. In opposite, on the other hand, in tantal nickel sulfur counterpart, the localized exciton phonon complexes causes local distortion, just local distortion that do not develop a long-range order here. So the difference probably reflects the different nature of ground states of these two compounds in good agreement of the excitonic insulator hypothesis in the case of selenium compound. In this case, this soft mode I show you, so it's already, so internal excitations in these exciton phonon complexes propagate like in acoustic mode. Yeah. So thank you for your attention.
Thank you, Alexander. Questions, comments? Yes, please.
Sulfur. Under high pressure, you can decrease the band gap, and you can make it even semi-metallic. Nothing happens in that process. Do you have any idea of that?
Now, I just mentioned that we are going to measure the spectra at uniaxial strain. But it's just
uniform hydrostatic pressure. You can find that the sulfur system can be semi-metallic without any transition.
Yeah, but we didn't measure in the high pressure, in the hydrostatic pressure. We can apply now. So uniaxial strain, it would be really interesting. I believe.
Another question.
Can you speak in the microphone?
Oh, sorry.
Yeah. In the beginning of your talk, you cited our paper, Sugimoto et al. And there, we argued that the peak, in the anomalous peak in the sulfur selenium system is due to the electron-hole attractive interaction, or that is electron-electron repulsive interaction. That is a very simple scenario, I think. And how do you think about that?
Which actual excitation?
In your first or second slide, you showed that the peak, you cite the paper.
Yeah.
Yeah. And you also show the calculation, Sugimoto et al. Yes, that's one. We interpreted the low energy peak, 0.5, 0.4 electron volt peak. Selenium one. No, experimental data. Yeah, that comes from simply from the electron-hole attractive interaction. That is our argument. That's electron-hole attractive interaction. So that means that the binding energy simply binding energy of exciton, electron-hole.
Yeah, exactly what I was talking about, but I cannot really support this idea, so I can just say, okay, we observed this feature in our spectra, it's there, so, but what the origin of this feature, is it really purely electronic in origin, or you have to consider also lattice effect there, we cannot really argue.
Okay, thank you. So you are not to disagree with the discussion? With
no, I would just try, if you can actually, could you really consider lattice effects as well in your calculations, maybe you can really get better consistency,
thank you very much.
better agreement with our data.
More questions? Okay, if not, let's thank Alexander again and